Thank you very much for the invitation, and thanks to the organizers for all their hard work in organizing such an amazing workshop. Okay, so I will start with some setup. So throughout this talk, L will be a number field. With algebraic closure L bar. And absolute Galois group denoted by gamma L. Okay, for now, X over L will be smooth, projective, geometrically reducible variety. Quickly, it will become a product of elliptic curves. And I'll write X bar for the base change to the algebraic closure. Okay, so quickly to recall some notation that's already been introduced. Write bra sub 1 of X for the kernel of the natural map to the brow group of the algebraic closure. So this is known as the algebraic part. And the co-kernel, no, sorry, not the co-kernel, the image, this quotient, is known as the transcendental part. And that's what I'm going to be focusing on computing today for some products of certain elliptic curves. So of course, by definition, when quotiented by the kernel, we now get an injection into the brow group over the algebraic closure. And because we started with something defined over L, the image is in the Galois fixed part. Okay, so the algebraic part is fairly well understood in general. And usually this transcendental part is more mysterious. But we do know that it's arithmetically important. It can obstruct the Hasse principle and weak approximation, as shown by Harari and Wittenberg. And Cyril yesterday gave another example of a transcendental obstruction. So it is worth studying. Okay, so I said it's more mysterious, but how bad is it? So in some of the cases we care about, it's really not very bad. So state a result of Skor-Bogatov and Zahin, which tells us about the transcendental part for abelian varieties and K3 surfaces. So this is a finiteness result. So if X is an abelian variety or K3 surface, then the transcendental part of the brow group is finite. And so this means we can compute it prime by prime. We can compute the p to the n torsion for every prime p and every natural number n, and then we're done. But OK, of course, we need to have some bounds, because otherwise we'll never finish this calculation. We need to work out which prime powers can actually occur. OK, so with that in mind, I introduce some more notation. So for an abelian group A, I write AN for the n torsion. And A sub p infinity for the p primary part, so the union of all the p power torsion. And here p is a prime, of course. OK. So now I will go to the case of a product of elliptic curves. So I use another result of Skorobogatov and Zahin. I will state a lot of their results, so I will just abbreviate them as SZ from now on. So if we take two elliptic curves over a number field L, then for every natural number n, we have a canonical isomorphism of abelian groups. As follows. So here I'm writing E bar n because I mean the n torsion over an algebraic closure. And again, here I will write with bars to emphasize that I mean all homomorphisms from E to E prime, not just those defined over the base field L. But here I take the part which is fixed by gamma L. Okay, so that's for this side. And they also have a result dealing with this side. So they have a canonical isomorphism of gamma L modules. This is okay. So I think what you really want to compute is this side. This is actually the transcendental part of the Bra group. But sometimes it's easier to compute over this side and then use knowledge of which primes divide the co-kernel to say something about this side. So that's why both these results are useful. Okay, but you may be thinking, what's the point? So actually, we know that for abelian varieties with finite Tate-Shafarevich group, any obstruction comes from the algebraic part of the Brauer group. So why would you want to compute the transcendental part of the Brauer group for an abelian variety? Well, the reason is that if you have a map from that abelian variety to another variety of some degree d, then you can, at primes away from D, you can relate the transcendental part of the two varieties. So in particular, you might want to look at the Kummer surface attached to a product of elliptic curves. So if we have a dominant rational map of degree D between K3 or abelian surfaces over L as usual, then we get a map going the other way on the Brauer groups over the algebraic closure. So this map is actually surjective. It's a gamma L module Hom. So it preserves the Galois action. And the kernel is killed by the degree D. And In fact, in the case where we have an abelian surface and its Kummer, we can say even more. So again, this is Skorobogatov and Zahin. Okay. So in this case, we get an isomorphism again, this is gamma L modules. And we get an injection as follows. Which is in fact an isomorphism for odd n. Okay, so in a recent paper, Yeronimou and Skorobogatov used these results to study the odd order torsion in the transcendental Brauer group of a diagonal quartic surface. And they computed the odd order torsion, and then they computed the obstructions to Hasse principle and weak approximation. They showed there was no obstruction to the Hasse principle, and sometimes an obstruction to weak approximation, and it gave precise conditions dependent on the coefficients of the quartic for when that could occur. So the way they did that was by relating the diagonal quartic to a product of elliptic curves with complex multiplication, and then using these results. And it was a particular family of elliptic curves. It was twists of the usual elliptic curve with complex multiplication by the Gaussian integers. So they related the quartic surface to a product of quartic twists of this elliptic curve. So the reason it has quartic twists is because it has complex multiplication by Gaussian integers. Okay, so then a natural question is, can one extend these methods and results to products of other elliptic curves with complex multiplication? And this calculation, I think, was particularly nice and interesting because when you have quartic twists, you end up using quartic reciprocity laws, and very nice class field theory comes in. So one example which was particularly interesting for me was, okay, what if I replace this elliptic curve with one with complex multiplication by z adjoin a third root of unity, and then you'll get sextic twists and sextic reciprocity laws coming in. And but the important thing is that you get a lot of structure coming from the complex multiplication. You can use that when you want to apply these results. Okay, so that's the case I'm going to talk about today. So the related quartic surfaces have the following form. So in particular, these surfaces contain a line, x equals y equals 0. So there's no point studying the Hasse principle, but you can still study weak approximation. Okay, but for now, I will compute the transcendental part of the Bragg group, so I will just be in the realm of products of elliptic curves. I won't be thinking about surfaces. Okay, so some more notation. I want notation for my sextic twists. So I denote by E superscript A the elliptic curve with affine equation y squared equals x cubed plus A. So the first step is to get a bound on the prime powers which can occur in the transcendental part of the Bragg group. So I take a prime, and then I'm computing the transcendental part of the Bragg group for a product of two twists of the same elliptic curve. So first of all, once you go beyond 7, oh, sorry, I forgot to put. So I'm computing the L primary part here. So once you go beyond 7, you don't get any L torsion. For 5 and 7, you just get L torsion. So no L squared torsion. And for 2 and 3, you can possibly get L squared torsion, but no more. So in order to prove this, I used some previous work where I computed transcendental part of the Brauer group for product E cross E, where it's just the same elliptic curve E over any number field with full CM, so with complex multiplication by the ring of integers of some number field. Okay. So proof of theorem 3 uses the following result. So I've got an elliptic curve over a number field with full CM. And just for ease of statement, I'm going to only state the result for odd primes, but I have a very similar result for L equals 2. It's just a little longer to state, so I will leave it out. So I have to define an integer depending on L. Of course, it depends on capital E and capital L as well, which is going to tell us where to stop when we're applying this theorem to compute the transcendental part of the Brauer group. We need to know which power of n can we stop at. Oh, sorry, which power of L. OK. So this is the largest integer. Such that we have the following condition on the Grosson character over the composite field KL. So we want its image to lie inside this order for all primes Q of KL of good reduction for E and coprime to L. So at these primes, the Grosson character is unramified, so it makes sense to evaluate it on a prime here. OK, so then we have the following result for the transcendental part, L primary part. So because we have the same elliptic curve twice here, we just get endomorphisms, and the ring of integers here is the endomorphism ring of the elliptic curve. And this is Z mod L to the m squared if the CM field is contained in the field of definition of the elliptic curve, and it's just z mod L to the m otherwise. In the second case, I can also tell you a nice choice of generator. You can just take the image inside here of complex conjugation. So an element which fixes KL but doesn't fix L. Sorry, other way around. So it should be in absolute Galois group of L without absolute Galois group of KL. Okay. So it's complex conjugation on the CM field. I should say image of. So I mean the image in here. Okay. So now we want a good way to compute this integer m. And the next result will get rid of the Gaussian character most of the time. So I define another integer, depending on L, which bounds m from above and is equal to m most of the time. Although, unfortunately, it's not going to be equal in the case that we're talking about today with Cm by z adjoint z to 3. But still, an upper bound is what we need for this kind of result. We're just getting bounds on the prime powers here. So again, it's the largest integer, such that the ring class field attached to this kind of order so ring class field corresponding via class field theory to this order. And I want that ring class field to sit inside the compositum KL. So then M is bounded above by N with equality, so long as we don't have too many roots of unity. So we're asking for the units in the ring of integers to be plus or minus 1, but K is a CM field. So the only way that wouldn't happen is if K were Q adjoint I or Q adjoint a third root of unity. Okay, so that's actually our case today. So we only get an upper bound, but it's still good. And so why is this better? I took away a Gaussian character. I introduced a ring class field. Not everyone may agree that the situation improved. But the good thing about this condition with the ring class field is that we have a formula for the degree of the ring class field over K. So if we want to test this inclusion, the first thing we can test is whether the degree of the ring class field over K divides the degree of KL over K. So I'm writing down a formula for the degree. This is the class number. Quotienting by number of units in the ring of integers. And this is the Legendre symbol. Okay, and obviously, if we have this inclusion, then the degrees, one divides the other. Okay, so that's basically what we're going to use to get this result. Okay, so just to save me writing this product all the time, I just call it x. And so in order to apply this result, I just want to base change to a field where this product EA cross EB looks like a product of an elliptic curve with itself. My field L was a sextic twist, so I introduced the sixth root of A over B. So by X sub L, I mean the base change to L, and this is isomorphic to product of the same twist twice. So now I have an injection as follows. And I can apply theorem 4 to this guy, and so I get this Z0 L to the M squared because I let C3 be in here, it doesn't really matter. And I mean, the point is that this is killed by L to the M, so now I just have to compute N. And so what I'm going to do is compute N and just say that it bounds it from above. That will deal with most of the primes. So again, we have this inequality, so we want to calculate N. So we have to test this inclusion. So this degree divides 6. I was adjoining a sixth root. OK, so now we'll just use the degree formula. Say that for large primes, even when I put t equals 1 here, I get something which is bigger than 6. So I can't possibly have this inclusion even for t equals 1, so that means n equals 0. So for L larger than 19, so when I apply the degree formula for the ring class field, my discriminant here is -3. And so you can check that this is larger than 6 for L larger than 19. So the largest integer such that this happens is 0. So I'm going to skip 17 and 19 until the end and not say much about them. But for 11 and 13, this degree is less than 6, but it's equal to 4, which doesn't divide 6. So again, I get 0. For 5 and 7, the ring class field KL is OK. It's degree 2. So I have to test whether n could be 2. And this degree is 2L, which is greater than 6. So n is less than or equal to 1, and m is less than or equal to 1. And, OK, for 2 and 3, L squared is OK, but L cubed is too big. So here we get n is at most 2, and therefore m is at most 2. So the ones I missed out were 17 and 19. So I've now proved this result, except for showing that I get 0 for 17 and 19. Is it OK? Does someone have a question? OK. And I won't go into the proof for 17 and 19, but the point is, at those primes, looking at n isn't enough. So n could be 1. But in fact, by really using the Grossen character, we can show that m is 0. So for that, you have to use some nice sextic reciprocity, but I don't have time for it. The point is that we really know what the Grossen character is. There's a nice formula for the Grossen character. And so you can just test this condition. I'll have to put a proof box in quotes because I didn't quite finish. OK, so we got bounds. And so now for the primes remaining, 2, 3, 5, and 7, we want to actually compute this group. So again, I will denote its product of curves by x. And the 7 torsion, I can put the 7 primary part if I want, because I know that's just the 7 torsion from this result. So it's either going to be z mod 7 or 0. And the condition is as follows. So those of you who are familiar with the Euronimo and Skorobogatov paper on diagonal quartic surfaces will see that this is familiar. I mean, it's the completely analogous result of their computation for products of quartic twists of the elliptic curve with complex multiplication by Gaussian integers. OK, and for 5 torsion, I get something very similar. But 3 torsion is different. And the reason for that is that 3 ramifies in the complex multiplication field, Q adjoins E to 3. So it has a very different behavior. So I'm still going to actually get Z mod 3 or 0, but the condition will be different. It won't be kind of testing about inclusion into this subgroup in Q star mod 6 powers. So condition is a little more messy. So in order to get some 3 torsion, I have to have 4a being a cube inside Q adjoin sixth root of a over b. And I have some restrictions on what this field could be. I think it should either be Q adjoining the third root of unity, or some cubic extension. So this is and this, or this. But 2 is not ramified, so for 2 we will get similar result using criterion about this subgroup. And here we actually do get all the possibilities. So note here, we don't get any Z mod 9, which was a priori a possibility, but here we do get Z mod 4 sometimes. So Z mod 2 if it's in the class of a cube, but not this cube. And 0 otherwise. So I won't go into the proof of this, but it really is using the results I erased by Skorobogatov and Zahin, and just, yeah, studying these Galois modules. OK, and what else? Oh, yeah, so I wanted to say a corollary now. Just, like, if you study these conditions, you'll see that, for example, you can't have both 5 torsion and 7 torsion at the same time. You can't have both these conditions. But because the condition at 3 is somewhat different, you can actually get 3 torsion and 2 torsion. So yeah, just like putting all the conditions together, you can see that we actually get a cyclic group of order n for n up to 7. And all of them occur. Okay, so in the last few minutes, I want to say something about obstructions to weak approximation on the Kuma surfaces, but this part is really work in progress. So I was trying to work as much as possible before coming here to have as much to present, but yeah, it was quite hard. So I will present some partial results about the obstructions. So I think, to be on the safe side, I will put this theorem in quotes because I have to just completely check all the details. But I think that this is what happens. So I now write y for the Kuma surface, just the Kuma surface attached to this product. And I'm going to suppose that I have, that I'm in this case. So I have a 7 torsion element. So I have a 7 torsion in the Brauer group, which is not algebraic. And in fact, you can show that the algebraic part is just the Brauer group of Q here. And OK, so actually, from the result I wrote down, it's not clear that you actually get a 7 torsion element in the Brauer group, giving the 7 torsion element here, because a priori you could have something in the Brauer group such that when you multiply by 7, it becomes algebraic, but not 0. But in fact, actually, I could change this and write 7 torsion here and 7 torsion here. But, so OK, so in this case, such an element does exist. And as Martin pointed out, in order to get an obstruction to weak approximation, you just need a non-constant evaluation map at one place. And so that place here is going to be 7. Actually, we get surjectivity. And so we get a transcendental obstruction to weak approximation, given by this element. And in fact, I think that the evaluation map at all the other places will be just 0. So really, the obstruction only comes from something at 7. OK, so the proof uses exactly the same strategy as Hieronymo and Skorobogatov's argument for the prime 5. The reason for the similarity is that they were dealing with complex multiplication by the Gaussian integers, where 5 is split. And here 7 is split in Q adjoint third root of unity, And having a split prime is really nice. Things break down. The 7 torsion of the elliptic curve breaks down into 2 pieces, and various things factorize, and the computation becomes much nicer and easier. So the question is, what about 5 torsion and 3 torsion? Remember, it's the odd order elements that descend to give transcendental elements in the Brauer group of the K3 surface. So it's going to be harder because 5 is inert in pure join third root of unity, and 3 is ramified. So in analogy, again, with Hieronymo and Skorobogatov's paper on diagonal quartic surfaces, I expect the result for 5 to depend on the 5-adic valuation of A and B. So I don't expect to get something uniform like here, where as soon as you have a 7 torsion element, you get an obstruction. I think it will be in 2 cases. Sometimes you do, sometimes you don't. But the calculation will be quite hard, and I have to use a computer. So first I have to learn how to use a computer. OK, for 3 is ramified, which I think actually won't be as bad because, OK, at least the prime ideal 3 does factorize. You get the same factor twice, but you have a nice submodule inside the 3 torsion, which is the things killed by 1 minus the third root of unity, and you can use that to your advantage. So far, I just did that in the case where A and B are the same. But there will be 3 cases. Because remember, for when I have a 3 torsion element, this field Q adjoin the 6th root of A over B is either Q, which is the case where A equals B, the one I can do, and then Q adjoin zeta 3, which I think shouldn't be much worse, and then cubics. So again, the algebraic part is just as small as it can be. And again, assuming that I have a 3 torsion element in the quotient is the same in this case as having a 3 torsion element in the Brauer group. So then remember that we had to have the cube root of 4a sitting inside Q adjoin the 6th root of A over B, which is just Q here. So A must be 2 times the cube. And the evaluation map at 3 is surjective. So again, we get an obstruction as soon as we have a 3 torsion element in the case where A equals B. And here this is you only get this behavior at the prime 3. At all the other places, you get 0 evaluation mark. OK, so I think I'll stop there. Thanks very much.